Okay, just a bit of a mini lesson for what we have in the case of partial fraction decomposition, which will be used quite a bit in the determination of inverse Laplace transforms. Okay, and the topic goes back to both Math 171. You might have seen it in that course, or you might not have, but definitely it is mentioned in Calculus 2, and just a little bit of going over. And for partial fraction decomposition, say if you have linear factors in the denominator, okay, and we have, for this example, we have linear factors x plus 2 and x minus 9. These are the denominator factors, and we're looking at just splitting up this consolidated fraction in terms of individual fractions that will have these respective denominators. And you want to maintain a 1 degree difference between the denominator and the numerator. Okay, so we have both x plus 2 and x minus 9 are first order in x, and 1 degree less than that would just be constant. So we have a over x plus 2 plus b over x minus 9. Now, if you have, let's say, repeating linear factors in the denominator, and the linear factors we have at x and x minus 4, x repeats where we have x to the third, as well as x minus 4, which we have raised to the second. And again, the factors are x and x minus 4, so the numerator in each fraction will be a constant. So for repetition, so we're starting out with first order in each of the factors going up to the degree that is in the overall expression, and we're going up 1 degree at a time. So we have a over x to the first plus b over x squared, and we stop at c over x to the third. Now for the square of x minus 4, the decomposition will be d over the first order of x minus 4 plus e over the square of x minus 4. Now, in the case where we have the appearance of a quadratic factor, here we have, for example, we have 4x minus 3 all over x plus 3 quantity times the quantity of x squared plus 7. We have a linear factor with x plus 3, so we have just a constant a over x plus 3. Now we have for x squared plus 7, this is a quadratic factor since we have x squared at the front. And you're going to have 1 degree difference, again, between the denominator and the numerator. So in the numerator, we're going to have not just a constant, but an x term. And we go from the, in this particular case, you have 1 degree less than x squared, which would be x, and we have filling in, we have bx plus c. So you're looking at, in the numerator, you're going all the way down to a constant, but where the higher order term is going to be 1 degree less than the highest degree term in the denominator. And if you have both repeating linear and quadratic factors, say if you have 4x minus 3 over the cube of x plus 3 and the square of x squared plus 7, your factors are still going to be x plus 3 and x squared plus 7. So we have a over x plus 3 plus b over the square of x plus 3 plus c over the cube of x plus 3. So all 3 degrees of x plus 3, or to which x plus 3 is raised, will be covered. And with the square of x squared plus 7, the factor is still x squared plus 7. So maintaining a 1 degree difference, we have dx plus e over x squared plus 7. And the factor is still at x squared plus 7, but we're going all the way up to the square. And the numerator, we still have linear in x, where we have fx plus g. Okay, now let's say if we're looking at decomposing the following fraction. Here we have not just a quadratic factor, but we also have a cubic factor. And this is one that we cannot factor exactly into integer coefficients. And looking at the decomposition, okay, so you have x cubed plus 2x plus 1 as a denominator factor. And I want to maintain a 1 degree difference between the denominator and the numerator. So the numerator is going to be a second order expression. So I have ax squared plus bx plus c. And for the square of x squared plus 1, we have a repeating quadratic factor, so maintaining a 1 degree difference. So we have dx plus e. And once again, to get up to the square of x squared plus 1, we have the numerator terms will be fx plus g. And if I'm looking at decomposing, I'm going to multiply everything out by the cubic factor and the square of the quadratic. And so clearing out, we have x plus 2 is equal to this long array of terms. So we have this particular trinomial. You have all the terms be multiplied by, okay, the square of x squared plus 1. And you have for dx plus c, you have multiplied by x cubed plus 2x plus 1. And also 1 remaining degree with x squared plus 1. And that's for fx plus g. It is over the entire square of x squared plus 1, but we still have to distribute both fx and g over the trinomial x cubed plus 2x plus 1. So this is going to be your setup. And now we have, in the case of the zeros, there's only one that we have that is real, and that's just going to be 0 itself. So what I did here, okay, I have, in this case, I have 7 unknowns with the coefficients going from a to g, and just setting up for the various values of what we have for x. So what I did here, I just chose 0, and then I decided to go up one natural number at a time for the input. So I have 7 unknowns, and 7 equations will be in the mix. So so we have, in this particular regard, all right, so you have very high number of coefficients, and again, plugging each of the x values from 0 to 6 into this equation, set of equations, and from this, now we're going to have, in the process, we're going to have 7 rows, 8 columns, and again, everything with 0, 0, 1, 0, 1, 0, 1, that's in reference to the coefficients from the a to g terms, and the rightmost column is what we have each equation to be set equal. Okay, so when x was 0, we have equal to 2, x is equal to 1, we have equal to 3, and so on. And performing the reduced row echelon form, this is where we're going to have an array of 1s and 0s, and you have 1s running diagonally. And okay, so just kind of a brief mention, and we have, say, just for the running across, in case you have like a is equal to 3/4, b is equal to 3/4, c is equal to 5/4, and you have 0a, 0b, 0c, 1d, d is equal to negative 3/4. You have e also equal to negative 3/4, and we have f equal to negative 1/2, and we have g equal to positive 3/2. And just looking at what we have in the results, so we have for this ratio, okay, now you could split this up, separating the terms, but just leaving what we have here. So you have your ax squared plus bx plus c, and you got dx and e, as well as fx and g. Okay, so those would be your coefficients once we put back into the decomposition setup for this particular ratio. And in the process, okay, so I used a TI-84 Silver Edition calculator. And again, so we have going into matrix, okay, you have editing, and you have the dimensions will be 7 by 8, so you have 7 rows, 8 columns, and I put in the coefficients. And after doing that, I went back to the matrix menu, selected math, and you had the reduced row echelon form. And again, choosing the matrix A, which is that 7 by 8 array where we had the last column to be the values to which each equation will be set equal. And then in this particular case, all right, so you have reduced row echelon form, so you have 1s to be running diagonally. And we have at the very end, okay, you have the decimal values, you have 3/4, 3/4, 5/4, negative 3/4, negative 3/4, negative 1/2, and 3/2. And that is from which we have the partial fraction decomposition results.